Okay, I think we can start. Hello, everyone. Hello, guys. Welcome one more Tuesday to our Processing in Memory course. Today, we are going to continue learning about real-world processing in memory architectures. And this probably won't be our last lecture talking about real-world processing in memory architectures, but at least today we are going to cover like some microarchitecture details about from one of the recent Samsung processing in memory architectures, the AXT one. In the previous lecture, you remember that we talked about film DRAM. Today we are going to talk about AXT. And yeah, very briefly remind you what we discussed in the previous lecture. It was this Samsung film DRAM that was announced in February this year, and it's a let's say application-specific architecture, or at least an architecture that is focused on an important domain of applications: AI, neural networks, etc. You may remember that the other day we also gave a little bit of background on the HBM memory, because this film DRAM architecture is based on HBM. It uses HBM. As you may remember, HBM is a 3D stack memory design that contains DRAM layers and a buffer layer at the bottom. Here in this figure, you can see two cubes of HBM, or two stacks of HBM memory with the DRAM layers and a buffer layer at the bottom. The buffer layer is directly connected to the host via this silicon interposer. And the way to access from the data from the layers is by using these vertical connections that are called through silicon vias, or TSVs. Regarding the internal organization of the film DRAM system, what we have is in each of the HBM layers, we see what we can identify that Samsung folks have placed these PIM units in between of two banks. And actually each of these PIM units can have access to two of the banks, one odd number and one even number bank. And if we take a closer look, we will see one of the banks here in this part of the figure, and this array of this SIMD array of FPUs, floating point units. In total, there are 16 floating point units, and they are 16 bits. And that's what we saw in our previous meeting. Sorry. Today, we are going to talk about the other proposal that we learned recently from Samsung. This is called the AXT system, and as you can see, AXT is a DIMM-based solution. In this commercial picture that we see here, we can identify DDR5 chips, so that's why we assume that the commercial product will be DDR5 PIM, but the version that we are going, or the prototype that we are going to study today, is based on DDR4. I don't think that there will be many differences in the fundamental things that take part of this design, and probably it's relatively easily exportable to DDR5. The use case that we are going to study today is a recommendation system, Facebook's DLRM, as you will see. And this is the paper. This talk is, this lecture today is based on this paper that you can access through this link. It's recently published at IEEE Micro. And yeah, near memory processing in action, accelerating personalized recommendation with AXT. Let's first, because recommendation systems are the use case today, are the focus of at least the implementation of this AXT architecture that we are going to discuss. Let me very briefly give you a short overview of recommendation models, and also a little bit of analysis on what are the performance bottlenecks of the different parts of the recommendation system and what parts are actually going to be more relevant and more interesting to us because they are going to be suitable for processing in memory. As I said, today we focus on this Facebook's DLRM recommendation system, deep learning-based personalized recommendation model. As you can see in this overview here, it has different components, and some of these components have already been diagnosed as computation dominated or communication dominated or memory capacity and bandwidth dominated. As you can imagine, this is where we are going to focus our interest today. Actually, we can already identify here the inputs, these dense features that are continuous inputs coming from vectors and matrices that are in memory, and they are typically processed by using DNN layers, as you can see, this bottom fully connected layer or this top fully connected layer that are computation dominated, as you can see. However, there are also sparse features that are for categorical inputs, and they are processed by indexing large embedding tables. And this is the part that is more relevant to us. As you can see, there are some operations here like table lookups and pooling, and these operations typically have or typically expose a gather reduce pattern, meaning that the processing element needs to access data on the CPU if we are, or GPU if we are executing this on a conventional processor-centric architecture. We need the processor, we need the processing elements gather the data from different parts of memory and then reduce them all together. And this is done in, for example, the Café2 framework by some operators called sparse lengths. And as you will see, these are going to be the relevant and interesting operators that we are going to target today, and the focus of the AXDIM system. We can do some performance characterization of this DLRM system and to identify key performance bottleneck. There are three different plots. In the plot on the left, you can see this two-dimensional representation of the memory footprint. On the y-axis, analytical memory byte is the memory footprint of each of the individual parts of the application of the recommendation system, and also the analytical flops, floating point operations per second. The different dots correspond to different batches, depending on essentially what's the size and what's the amount of parallelism that the input has. The darker the color, the larger the batch. Actually, here on the right-hand side, you can see what are the actual numbers of batches for each of the different colors. And so one thing that we can observe in this leftmost plot is that the analytical flops are quite low in these SLS operators compared to other other layers of the system, and also that the memory footprint is pretty high, especially for larger batches, right? Then if we look at the plot in the middle, which is a roofline model for all these operators, we can also see how low the operational intensity is for these SLS operators. So they are clearly in the memory bound area of the roofline. And also, they don't even manage to achieve more performance than what is provided by the bandwidth. So not very good exploitation, for example, of the cache hierarchy of the CPU. So interesting observations here are first that the floating point intensity is pretty low for these SLS operators, and second, that larger batch size implies larger memory footprint and also memory intensity is what we can see here on the leftmost plot. And also, if we look at the rightmost plot, which represents the bandwidth for different numbers of parallel threads executing the SLS operators, what we see, and it happens essentially for all batches, all sizes of the batch, we see that the bandwidth saturates pretty quickly as we increase the number of parallel threads executing the SLS operators, right? And these bandwidth saturation is a good indicator, and also, of course, the high memory intensity, memory footprint, and low arithmetic intensity that we have observed with the other plots. These are all very good indicators of PIM suitability, right? So it really makes sense to come up with some ways of executing these SLS operators near the memory. And there have been actually several papers targeting this problem and trying to optimize personalized recommendation systems by using processing in memory. One of the most relevant ones is this RecNMP that was presented at ISCA 2020. You can find the title at the bottom of the slide. And essentially, this RecNMP exploits rank level parallelism. It's a DIM-based NMP architecture similar to the AX DIM that we are going to discuss soon. And the key idea is to multiply the bandwidth by exploiting rank level parallelism. As you can see, the embedding entries, the input to these SLS operators are fetched from the concurrently activated banks. Observe that if we have twice the number of, so if we have 2 ranks, we can multiply the bandwidth by 2, but the good thing is that we may have even more ranks in every channel, so we could be operating on all these different ranks at the same time. And then these embeddings that are accessed from the ranks are processed by this NMP processing unit that resides on the DIM as well. So these local embedding lookup and polling functions are executed at the memory side, producing this gather reduce execution pattern that I mentioned before. Please let me know if there are any questions. So after performing the computation on the NMP processing unit, the final pooling result will be transferred back to the host using the conventional DDR interface. And the computation that essentially happens here in the NMP processing unit for these SLS operators is an element-wise summation. So as you can see, it's a relatively simple operation, low arithmetic intensity, because it's just addition, but also very highly memory intensive, makes it very suitable for processing in memory and for a system like this DIM-based architecture. So the thing is that RecNMP and other similar proposals have been tested in simulation, for sure, providing very interesting and promising results, but there was no prototype, and that's what these folks in their paper, Samsung and Facebook folks, try to deal with in their IEEE micro paper, and also at the same time creating a prototype for hopefully soon real world and commercially available system. So this Accelerator Beam is a DDR4. As I said, this is the realization in the paper, but future AX-DIM devices might be, and apparently is what it looks in the commercial picture that I showed before. Might use DDR5 memory, but for now this is DDR4 compatible FPGA-based platform with standard memory interfaces. And this is it can be a prototyping platform for near memory processing, not only for this type of problem recommendation systems, but maybe for many other different workloads that could adapt well to this kind of system. And this is potentially possible because the system itself, the AX-DIM itself, can support specialized accelerator modules, as the case that we are analyzing today, but also it can support in general, in order general purpose processors, probably something simple like ARM cores, or maybe something similar to the architecture of the Upman GPUs. But for sure there will be low power and relatively wimpy processors, but the fact that you have a lot of memory in the system, many different DIMMs can multiply the available hardware parallelism in the system. So as I said before, today the case study for this architecture is a personalized recommendation system. Today in this lecture, we are only going to cover the hardware implementation part. We may talk about the software stack support in a later lecture. And this is an overview. I'm going to show you here in this slide an overview of the system, the complete system. So the first picture that you see on the slide is the baseline system. This essentially contains a CPU, and then there are DIMMs connected to the CPU via four memory channels. The AX DIMM system replaces two of these DIMMs with AX DIMMs containing DDR4 chips, and one FPGA each. And there is where the processor, the central, the host processor is going to offload the computation of the SLS operators. And this is another view, another picture of the system with the two DIMMs that you can easily identify. Okay, so let's take a closer look at the hardware architecture. The first thing that we can see on this AX DIMM design is that it has a standard DIMM interface. This is really good for the integration of the AX DIMM design on a real system, for an end-to-end integration, because the CPU can interact with the ranks and with the accelerator that we will place here in the FPGA by using the standard DIMM interface, and as actually you're going to see soon in later slides. Also, similar to previous proposals like this RecNMP that I mentioned, it exploits rank level parallelism. This way, the two DRAM ranks on the DIMM can be activated simultaneously, can be activated in parallel to load embedding entries from memory. And then inside the FPGA module is where we will have a couple of near memory processing units that will perform this element-wise summation with the data that is being gathered from rank 0 or rank 1. And this is a view of the internals of the design on the FPGA. Yeah, sorry. If we take a look at the internals of the FPGA, we can identify these two NMP units, one for rank 0 and the other one for rank 1. And as you can see, they can access each of the ranks directly. Let's take a closer look at each of the individual components in this special function unit or accelerator that we have for the SLS operators of recommendation systems. So the first thing that we can find here is the DDR4 slave interface to receive DRAM commands and NMP instructions via the DQ pins from the host side. So the host is using the DDR4 interface to communicate with the accelerator. But the way of doing this is by using conventional DRAM commands, as you will see. Even not only the data that will be copied to the ranks, but also the NMP instructions and the commands to start the computation on this accelerator here, on this pipeline. We are going to see how. We can also identify here two interfaces, one for each of the NMP units to access the corresponding rank. We can call them memory interface generator, but this is essentially like the interface that handles the accesses to DRAM, to rank 0 or rank 1 from the NMP units. And here we can also see in this plot that it's possible to work with two different execution modes. The first execution mode is the non-acceleration mode. This is simply no acceleration. This is simply memory access. So the host processor can access the ranks in a conventional way, just to read and write data as it usually does with any other DRAM device. And then we have the acceleration mode. In the acceleration mode is where the NMP elements come into play and they start accelerating the workload, in this case, the SLS operators. One important thing to remark here is that the acceleration mode is blocking. And what this means is that when we are in the acceleration mode, the NMP units in rank 0 and rank 1 can access data in the corresponding rank, but not the host CPU. So while we are in the acceleration mode, the host cannot access the DRAM. Observe that this is similar to what we have seen in other real-world processing in memory architectures. In the AppMem-based PIM system, we also have the host CPU having access to the MRAM banks of the DPUs at the very beginning of the program or at the end of the program. But while the DPU is executing the corresponding processing in memory kernel, the CPU cannot access memory, the MRAM banks in the case of the DPU, the AppMem system. Okay, this is the format of the instructions, the NMP instructions that are loaded into this instruction buffer and later executed onto this pipeline. We can identify some of these 64-bit instructions, and we can identify different fields here in this format. There is no comprehensive explanation about all these different fields in the paper, but you can imagine what they mean, right? So for example, here we have the opcode is 2-bit opcode, so probably we cannot have many different instructions, but also it's not the intention in this architecture, right? So with an opcode of 2 bits, we can only have 4 different instructions. It might be possible that some of other bits, like for example, the reserve bits here could be used later for some func field, similar to what we have in MIPS for MIPS architecture for the arithmetic operators. So the fact that we only have 2 bits for opcode doesn't mean that we can have more than 2 instructions and operations executed on this pipeline. And we can identify other fields like row address, column address to access the data that is needed from the ranks. The way to offload these operations from the host to the NMP units is by using read and write operations from the host processor. As you will see, the host processor first writes all these instructions that correspond to the program that is also uploaded to the processing memory side onto this instruction buffer. And this instruction buffer in the current implementation has a size of 256 kilobytes. So you can see it's actually quite a large instruction buffer. And we also have a partial sum buffer of the similar size, same size. This partial sum buffer is to store intermediate values for embedding pooling operations. So whatever is being computed here in this part of the pipeline will be written back to this PSOM buffer for storing the intermediate values, intermediate calculation results that might be later being used by the rest of the pipeline, or written back to the host as when the computation finishes. We are going to see when this happens. Then another thing that we can identify here in this pipeline is this instruction decoder. This instruction decoder essentially fetches instructions from the instruction buffer, decodes them, and then sends the corresponding signals to the rest of the elements in the pipeline, for example, this command generator or the other array. And the command generator is the unit that is in charge of issuing read commands to the DRAM banks or to the corresponding DRAM rank and the PSOM buffer. Why is that? Because we need to access data that is going to be added by using this other array here, right? And recall that the operation that is being executed is a element-wise addition, and for the element-wise addition, you need at least 2 elements per lane, right? And that's why we need to access simultaneously the rank and the contents of the PSOM buffer. In particular, the bandwidth that is achieved here is 64 bytes from each of these, either the rank or the PSOM buffer in one cycle. And then in the other array, we have 16 32 32-bit floating point adders that perform the element-wise summation of the values that are coming from the embedding tables and the PIM vector. So these are like the different components that take part of the internals of this FPGA. The good thing of having an FPGA here is that it's programmable, so we could use it to, that's why the AX team is good as a prototype. We could use it to also implement different specialized function units that could be useful maybe for this workload recommendation systems or something else. But today we have the recommendation systems as the use case, and actually is a very good one very good use case to discuss all the possibilities of this kind of processing in memory system. Maybe some of you might be asking, okay, how is possible for the host by using simply conventional DRAM commands to communicate with the NMP units, configure them? Notice that we have here non-acceleration mode or acceleration mode, so we need to have some, the host needs to have some capability for reconfiguring this execution mode, but then we also need the host to be able to send the instructions, the program, to this instruction buffer, and also to read the results from this PIM buffer, right? And all of this is possible because of, or thanks to the address map or memory map of AX-Team. So all these registers, the PIM buffer, the configuration register, or the instruction buffer are mapped to memory and they are accessed by the host as if they were addresses in the DRAM ranks. Actually, as you can see, this bottom part of the address map corresponds to the ranks themselves where the embedding tables are going to be stored. And now we can take a look at the execution flow. How is the execution being done in this system? Notice that here on the top we have rank 0 NMP, the processing element corresponding to rank 0, and here we also have the other one corresponding to rank 1, rank 0 here, rank 1 here, with the corresponding components of each of them. And we are going to see these step by step. At the bottom, in this bottom part of the slide, what you can find is a timeline of the execution. And it's divided into two parts. In the upper part, or this middle part here, is the execution, what is happening in the host. And then at the bottom part, we have the different operations that take place, or the different pipeline stages that take place for execution of instructions on these rank NMP units. So the very first thing to happen is in the non-acceleration mode. Notice how the host is accessing the ranks to store the embedding table. So this is a write operation that is taking place from the host, non-acceleration mode. So the rank NMP unit has nothing to do here yet, and that's the way of writing the embedding tables to the ranks. Then in step 2, the processor, the CPU, the host processor needs to change the mode from the non-acceleration mode to the acceleration mode. And to do that, it needs to write certain value, let's say a flag, to activate the acceleration mode here in this configuration register. And as soon as that's done, then the processor can load the program that is loaded to the instruction buffer of the NMP unit, and it's essentially the kernel that is being offloaded to the memory side. And at that point, the execution on the pipeline can start. So the very first thing is for the processor to also launch the kernel, and this is done by writing the configuration register as well. As you can see here, this orange arrow that goes directly to the configuration register. Once setting the corresponding value, the corresponding bits of the configuration register, the execution can start. So we will have this decoder here fetching a new instruction, previously loaded instruction into from the instruction buffer, decoding it, and sending signals to the rest of the components. And that's what we observe in this part of the timeline for all the different instructions. Notice how the execution of all these instructions is pipeline. We have first the decoder reading an instruction from the instruction buffer and decoding it, and then we have two operations happening in parallel, done by this command generator that we have here to access both the PSOM buffer and access also the embedding tables stored in the corresponding rank. And after that, the 16-lane SIMD unit, the other that we have here, will perform the addition for each of the elements that are being accessed from the rank and the PSOM buffer. And after the additions are completed, the results are written back to the PSOM buffer in this accumulate stage, or this write back stage that you can see at the very bottom of the image. In the meantime, what is the CPU doing? Recall that the acceleration mode is blocking, right? So the CPU cannot do anything else with this memory in rank 0 and rank 1. So in the meantime, what the CPU is doing is calling the system to check whether the computation finished or not. This is also, remember that something similar was done by the CPU in the admin-based PIM system. And the way to do that for the CPU is to check this status register. The status register is also in the configuration register, and it's being accessed frequently by and read by the host CPU to see if the computation finished or not. And finally, after the computation is done, the kernel terminates all these execution of instructions, pipeline execution of instructions in the NMP units finish, and the PSOM final result is ready for the CPU to read from the corresponding address, pointing to this PSOM buffer and reading the final PSOM value that is used in later stages of the recommendation system. This is all for now about this architecture, but you can read more about more details than what I gave here in the paper. You can access from this link. So as you can see, there is a very promising landscape and very promising future for processing in memory systems. We have been in these 4 lectures talking about existing processing in memory systems. Probably in the next edition of this course, in the next spring semester, we will be talking about more details about these architectures, and also probably new architectures as well. It is at this point, is I believe, a very hot topic, and also very exciting to see how computer architectures and how computing systems are evolving thanks to the shift to this processing in memory paradigm. Very recently, actually this month, I learned about another company that is fabricating processing in memory systems. This company is called Neuroblade. It's a startup from Israel, and even though I don't have many much information about them, don't really, if you check their website, won't find a lot of details about how the system is built, but at least we can know that these are processing in memory chips that combine DRAM and cores. They say an approach similar to GPU. It's similar to GPU for sure, because of the fact that it has thousands of cores, so it should be good at exploiting data level parallelism. And according to their website and the information that I found in this piece of news, this it's an architecture intended to optimize the execution of AI software and also data analytics. So it's for sure a very promising architecture as well. As I said, there is not much information that I could find, but one thing that I found is this pattern. I don't know by how much the pattern really represents the actual system, but it can give us a few ideas about how this build, how this is built, and also it's interesting to identify what are the commonalities and also differences between this processing in memory system and other processing in memory systems. If we check at the abstract, we can see that this is a distributed processor. It's something that we can guess, and actually it's something common in many different, in all different processing in memory systems that we have seen so far, because you have different processing elements and each of them has access to its own memory space, typically DRAM chip or DRAM bank, or maybe several chips, as in the AX team, a whole rank, as we have just seen. It is a distributed processor with memory arrays and processing arrays. And these processing arrays are composed of processing or processor subunits that each of them is associated with a corresponding and dedicated memory bank out of a plurality of discrete memory banks. So as you see, similar approach to the ones we have discussed in previous lectures. But something kind of different, apparently, according to this abstract, from this architecture is that the each of the processor, these processor subunits, is connected to other processor subunits. So it seems to be directly connected. Actually, if we take a look at this picture that is coming from the pattern as well, where we can identify different memory instances, I guess this will be memory banks. Near them, we have processor subunits, and we can also see these direct communication channels in this system with 4 processor subunits. We see that they are connected all to all, right? And yeah, this kind of interface can be for sure very useful for many important workloads as well. Recall in the admin-based PIM system, for example, the overhead, the existing overhead for communication across DPUs, because all communication needs to go through the host system, through the host processor. And from another picture from the pattern, we can go a little bit deeper and see that near this memory instance, we have the processing element or processor subunit that it's called here, and here we may have processor element. Probably this is something like more general purpose low power processor, and then some accelerators as well. But this is, hopefully in the next edition of this course, I will be able to explain more details about this Neuroblade and many other new architectures as well. Just to wrap up about all these different real-world processing in memory systems that we are studying, let's very briefly recap on similarities and differences among these current systems. So similarities, something that is common in all of these is that they follow what we call a processing near memory approach. Why is that? Because essentially all of them are placing processing elements near the memory arrays, either the bank, either the memory rank, as in AX team, but it's a processing near memory approach. It's not going even closer to the memory cells and computing with the memory cells themselves, as some of the proposals that we discussed in our first lecture, the first lecture of this course, what we call processing using memory. And then there are differences. So for example, some of them are near bank and others are near chip. So near bank are AppMem and FinDRAM. Near chip is the AX team system that we have presented today. Then also some of them are general purpose and others are a special function, right? In the case of AppMem, we talk about general purpose processors, small, wimpy processors, but still with a rich instruction set and general purpose, capable of executing any type of workload, essentially. And then we have something that is more special function, because the target was a specific class of applications and specific operators in these applications, such as FinDRAM, or also the realization of AX team that we have presented today, because it's specialized hardware that only executes these SLS operators from the recommendation system. But as I said, AXTeam is also a prototype, and as indicated by the authors themselves, it can also replace the special function units with more general purpose processors that can be used for different workloads as well. Then the different processing elements or the different compute units that we have near memory exploit different architectural paradigms. In the case of AppMem, recall that it's a fine-grained multi-threaded architecture. We have a single in-order pipeline in each DPU, and we have different hardware contexts for different hardware threads, so they can run multiple software threads at the same time concurrently, right? And by using this fine-grained multi-threading architecture, it's possible to hide latencies of memory access or execution in the pipeline. We discussed this, the way that these AppMem DPUs operate in our third meeting. And then we also have the SIMD paradigm in FinDRAM or AXTeam, the way that we have seen them in the current implementations that we are aware of, right? In the case of FinDRAM, we have 16-bit SIMD lanes. In the case of AXTeam, we have 16 32-bit SIMD lanes in each of the NMP units. Then about the data types and instructions that they support, as you may remember, AppMem is a natively integral computation, even though some multiplications or additions, for example, are not supported natively. For example, 32-bit multiplication, integral multiplication and division are not supported natively. But overall, it has many different natively supported integral instructions. It also supports floating point computations, but as you may remember, is by emulating these floating point operations. However, floating point data type is the native data type in FinDRAM and also in the implementation of AXTeam that we discussed today. The difference between them is FinDRAM is using floating point 16, while AXTeam in this implementation is using floating point 32. And then another difference across all these types of memories is the actual memory that is being used, right? In the AppMem, it's a DDR4 DRAM memory. In FinDRAM, it's HBM2. In AXTeam, it's DDR4 in the implementation that we have discussed today, but apparently they will release at some point some DDR5 implementation, as we have seen from pictures from Samsung. So these are important differences. I mean, probably these the actual memory technology that is being used is not so important at this point. In principle, there's no reason for not being able of embedding an AppMem DPU, for example, in HBM2, or the type of SIMD units that FinDRAM uses in something like a DDR4 or DDR5 memory. But we will probably see many of these combinations in the future as well. Okay, so as I said in the previous slide, the real-world processing in memory architectures for now are following this processing near memory approach, where the processing elements are placed near the memory, but not inside the memory arrays themselves, right? There are, as you may remember from the first lecture in this course, that there are also some promising and very interesting proposals that we call, or we encompass, we group all of them into something that we call processing using memory, because in this case, the computation is done by the DRAM cells themselves, the memory cells, or DRAM specifically in some of the proposals that we explained, like row clone, ambit, etc. And essentially, these processing using memory consist of taking advantage of the analog operation of memory, of the memory cells, and by using this analog operation, perform some sort of computation, right? You may remember, I mentioned them, proposals like row clone to copy one row in one subarray, another row in the same DRAM subarray, or AMBI that consists of activating 3 rows at the same time inside the same subarray to perform a majority operation that can be used for other logic operations or arithmetic operations and so on. So far as I know, there is no real system taking advantage of these techniques to execute computation inside memory. But at least what we have seen is a very interesting proof of concept that was published a couple of years ago in a micro conference, and it's this compute DRAM paper that I would definitely recommend to everyone. The main reason for that is because these authors figured out a way of executing operations similar to row clone or AMBI by using off-the-shelf DRAM chips. I'm not going to give you many details about this work today because we are going to talk about it in more detail in our next lecture. But I want to very briefly introduce it now. The way of doing, the way of implementing these processing using memory techniques in these off-the-shelf chips is by using an FPGA-based memory controller that is actually a product from our group, and you can access it by using this link. Is SoftMC. Is a, as I said, is a experimental platform, is an FPGA-based memory controller for characterization of DRAM chips and DRAM-related studies. And the authors of Compute DRAM use it to be able to play with the timing parameters when operating on these real DRAM chips that, as you will see, you can buy them yourself. So, and yeah, so these 2 figures here explain more or less how a row copy operation, kind of row clone operation, copying one whole row into another row inside DRAM, or also how to activate 3 rows at the same time in order to execute some logic operation, like an AND, for example. Let's take a quick look at what they do. So in the figure, you can identify this is essentially one bit line. In the bit line, we have 2 rows. This is the capacitor of this bit line in, let's say, row 1, and this is the capacitor of this bit line in row 2. And each of these are different steps in this timeline that you can see here at the bottom. So at the very beginning of this operation, we have this capacitor here that is fully charged, and at some point the corresponding word line is activated. So as soon as the word line is activated, the capacitor starts leaking charge onto the bit line, and in this step 2, you see how the bit line, the bit line voltage is perturbed by the charge in the capacitor, and this is why we see that the voltage level of the bit line starts to increase. At that point, we activate the sense amplifier, and this restores here the charge of the capacitor and puts the whole bit line to VDD. So at this point, we have the highest voltage VDD in the bit line. And at that point, we can activate another row. Notice that if we reduce these latencies for the this second activation, the activation of R2 in this step 4, we will be at a point where the voltage of the bit line is still over half VDD, as you can, it's represented by this, by the picture, by this figure here. And what this means is that by activating the cells in another row, we start charging, or we start adapting the charge and the voltage of this capacitor to the voltage of the bit line. If at that point we activate the sense amplifier again, we will end up moving the voltage of the bit line again to VDD and charging completely the capacitor in the other row. So this is the way of doing row copy in compute DRAM. It's pretty similar to the operation of row clone that I explained in the first lecture, but it's only playing with these timing parameters T1 and T2. And the way of doing it needs to violate the JEDEC standard, but still it's something that is definitely doable, right? And it's something that we can control ourselves, or the authors of Compute DRAM did, by using something like an FPA-based memory controller similar to or like SoftMC. Yeah, these are the different steps that I explained, and here we have a similar operation, but in this case it's performing bitwise AND. We have an initial row R3 here. No, so sorry, it's R1, the row that is first activated, then pre-charge in a very short time. Notice that these T1 and T0 are essentially 0 idle cycles. These T1 and T2 are essentially 0 idle cycles. This T2 is very short, so the pre-charge command cannot close R1 completely, and then R3 will appear on the memory bus. This is due to the way that the row decoder works. This R3, which is in principle not intended to be activated, appears on the address bus for just a few picoseconds, let's say, and this makes that the R3 row is activated, but also R2 is activated, and the actual effect is that the 3 rows get activated in a very, very short period of time, essentially the 3 of them at the same time. And even though this is not exactly doing the same thing as Ambit did, Ambit, remember, extends the different subarray with a row decoder that is able to activate 3 rows at the same time. Even though the implementation is not the same, because this is just using and changing the timing parameters, it produces a similar effect. As I said, you will learn more details about this work in our next lecture, and we will explain all these operations in more detail. Here you have some information about the experimental methodology, the SoftMC software and SoftMC hardware here, as I mentioned before, and these are the evaluated DRAM modules. In total, 32 DDR3 modules, around 256 DRAM chips, and here is how this proof of concept is carried out by using the SoftMC, how the experiment is being done. First, well, filling the subarray with random data, and then issuing these sequences of activate, pre-charge, activate with different T1 and T2 parameters, and then see what are the results. And turns out that you can definitely perform a row copy operation, and even in some of the chips, ambit operations, triple row activation to perform computation. And these are the results for different chips. Each of these squares here represents different chips from different vendors, as you can see. And the X and Y axis represent the possible timing parameters for T1 and T2 in number of cycles. As you can imagine, this doesn't work well in all cases, or not perfectly well in all cases, but there are several chips where all row copy operations are done okay, 100% success, no errors. For example, here for these SK Hynix chips, or here for this Micron chip, or here as well. and these are the blue colors, correspond to the row copy operation. For and over operations in the ambit-like style, it's not so frequent that this happens in real chips, but still in some of the cases, for example, in this case here is 100% success. So this is definitely promising. And one final thing that I would like to highlight here is that it's not about being able to actually use these real chips, off-the-shelf chips in our system and start using them for computation. I think that the true value of this work and all this experimental analysis here is the fact that it's a proof of concept. Even if the chips have not been built with the possibility of doing computation with them in mind, it's possible to do computation with them. And it's possible at least to move data reliably internally to a different subarray in many of the cases, as you can see. So I think that there is definitely something promising in this direction of processing using memory with DRAM. This is the paper, again, very recommended, highly recommended reading. And in our next lecture, we will talk about it in more detail. Actually, we are going to present an end-to-end system that can make use of these kind of techniques to, even go further in the development and the process of enabling processing in memory in computing systems. And maybe some of you might be asking yourself, okay, what if we put in the same system processing near memory capabilities and processing using memory capabilities? That's for sure something that will be possible at some point, and it's definitely something really promising. Working synergistically, having different types of processing in memory working synergistically. And very recently, we have presented this paper at Micro. SISA is a set-centric instruction set architecture for graph mining, and it has been implemented by using as I said, a near memory processing approach or processing near memory approach, where some compute elements are placed near the memory arrays, but also by exploiting ambit-like computation, this idea of activating 3 rows at the same time to perform a majority operation can be also an AND or an OR operation, and can even provide a functionally complete set to implement even more complex operations as well. So this is actually the first work I'm aware of that combines both processing near memory and processing using memory, and as you will see if you take a look, produces very interesting performance and energy savings results for graph mining algorithms. So this is all for today. In our next lecture, as I said, we are going to talk about processing using memory with DRAM and end-to-end system integration of processing using memory techniques. We will have our student Ataberg Olgun, who is working on this project, and he will give you a comprehensive presentation and explanation of this end-to-end system. And in later lectures, we are going to continue with workload characterization and also programming aspects of real-world processing in memory systems, with probably a special focus on the PIM architecture. So this is all for now. If you guys have any reason, please have any question, please let me know. If you guys, if you don't have any questions, then I think we can finish the lecture for today. I'm trying to check whether there are any questions here in the YouTube chat, but I don't see any question. I don't know if it's because the connection is not very stable at this point. Yeah, but anyway, if there are questions, please don't hesitate to reach out and I will try to answer them offline as well. Thank you very much for your attention, and talk to you